Thank you for the introduction and thank you for the invitation. So as mentioned, my name is Ken Wong. I'm an assistant professor at the University of Tokyo. So I'm originally from the US, but I've lived in Tokyo for quite a long time now, over 9 years. I've been at the University of Tokyo for about a year and a half now. So at the University of Tokyo, we have a few different departments and institutes. So we have a Department of Astronomy, Department of Physics. Some of you may have heard of IPMU, the Institute for the Research for Physics and Mathematics of the Universe. So actually, I used to work there. That's actually on a different campus, but it's affiliated with the university. And my institute is RESCEU, the Research Center for the Early Universe. So it's just in the building next door to the Department of Astronomy and Department of Physics. So actually, I'm a little bit out of place research-wise there because I'm more of an observational astronomer and cosmologist myself. A lot of people at RESCEU do things like gravitational waves and early universe theory. There's also some supernova people, but it's a good mix. And I spend some time at the Department of Astronomy and Department of Physics next door as well. And if anybody happens to be in Tokyo or even in Japan at some time in the future, feel free to contact me. And it's fairly easy to arrange a visit or a talk sometime. There's plenty of opportunities there. So my connection to CASSA is through my collaborator, Anwar, who I'm sure you're all familiar with. So we've worked together on strong lensing cosmology for several years now as part of the same collaboration. So that's what I'll be talking about today. And my understanding is that Anwar gave a talk about this project a couple years ago, but maybe some of the students were not in the audience at the time, so I will go over some of the basics again. And yeah, it's probably very early in the morning for him, so I assume Anwar is not here, but yeah, big thanks to him for arranging this. Okay, so with that, I think I'll just begin the talk about strong gravitational lensing and my work. So strong gravitational lensing is this scenario where you have a bright background object, which we call the source, that is being magnified by an intervening foreground object, which we call the lens. So we have this alignment between the observer, the lens, and the source. And if this alignment is good enough, you can get something that looks like these two things. Can you see my mouse cursor?
Yes, we can see the cursor.
Okay. So on top here, we have an example of a lens galaxy. So here you see the lens in the middle. It's this big elliptical galaxy. And this blue ring around it, that's actually a background star-forming galaxy that is being lensed into these multiple images and almost a complete ring here. And on the bottom, we have an example of a lens quasar. So quasar being a very compact point source. Here it's being lensed into 4 separate images. So 4 images of the same quasar, but you see these multiple images due to the strong lensing effect. Now, what we can do is we can say, okay, we know the light from each of these 4 images had to arise from the same position in the source plane. So we can ask the question, what is the mass distribution of the lens galaxy here that when we sort of reverse the lensing effect, will coherently map these 4 images back to that same point in the source plane. So this process is called lens modeling. And you can do it in a few different ways, but the idea is we're trying to reconstruct the mass distribution of this lens that can explain the observation. And because the lensing effect depends on the mass distribution of the lens and it's sensitive to all of the mass, not just the baryonic mass, but the dark matter as well. This can tell us something about the dark matter distribution of galaxies and clusters. So lensing is a good tool for that. It's also affected by line of sight structure. So if there happen to be some galaxies or groups or clusters along the line of sight, those can have induced perturbations on the lensing effect. So those we need to account for. And it also depends on cosmology because the distance that the light travels to get from the source to the lens to the observer, that distance is going to change depending on your assumed cosmological model. So our sort of standard model of cosmology is what's known as the flat lambda CDM model. So this is a fairly simple 6-parameter model where we assume there is no spatial curvature. We assume a dark energy equation of state W equal to -1. And we have these parameters omega matter and omega lambda, which describe the density of matter and what we call dark energy, respectively. And this fairly simple model has been successful at explaining a lot of observational data. And in particular, it's very good at explaining observations of the cosmic microwave background. So this image on the bottom right here is an image taken by the Planck satellite about 10 years ago. It launched, and their last data release was about 5 years ago. So this image from Planck of the CMB, this is the most precise image we have of the entire sky at this microwave wavelength. And this pattern of hot and cold spots that you see here encodes a lot of information about our underlying cosmology. So this tells us a lot about the density of various components of the universe. One thing that the CMB does not constrain, however, is what we call the Hubble constant, h0. So the Hubble constant is the present day expansion rate of the universe. So this kind of tells us how fast the universe is expanding today. And this is an important parameter because depending on how fast it's expanding, that changes, for example, the age of the universe, changes various structure formation scenarios. But again, this parameter is not directly constrained by the CMB. What you need to constrain it is you either have to combine it, the CMB, with other observations, or you have to assume some underlying cosmological model. So if you were to assume that flat lambda CDM is correct, then the CMB can tell you pretty precisely what h0 should be under that model. So in recent years, there's been sort of an emerging tension in different measurements of the Hubble constant. So that picture I showed you on the previous slide of the Planck CMB measurements, under the assumption of flat lambda CDM, the Planck CMB measurements can constrain h0 to less than 1% precision. So they get a value of 67.4 plus or minus 0.5 kilometers per second per megaparsec under the flat lambda CDM model. So alternatively, you can try to measure the Hubble constant h0 directly in the local universe. So there are several different methods of doing this, but the most popular and most precise method at the moment is what's known as the distance ladder. So this is using a variety of distance indicators. So for example, using some geometric measurements to get distances to some nearby galaxies, and then using some intermediate calibrator, like for example, Cepheid variable stars are a very popular intermediate step here, where their luminosity is proportional to their pulsation period. So once you can calibrate that relationship using some local geometric measurements, now you have distances to all these Cepheid variable stars. And then those in turn can calibrate brighter distance indicators such as type 1a supernovae. So these type 1a supernovae are thought to be explosions of white dwarfs, and they always have the same detonation luminosity once you correct for some metallicity effects. And so these standard candles are used in this sort of successive ladder. That's why it's called the distance ladder. So going from geometry to intermediate calibrators like Cepheids to these type 1a supernovae, this gets you distances to very far away objects within the Hubble flow. And so using this method to get distances and then the velocities you get just from measuring the redshift, you can measure the Hubble constant directly, the expansion rate directly. And the team that's been sort of leading this effort is the Hughes collaboration. And their latest measurement, they get a value of h0 of 73.2 plus or minus 0.9 kilometers per second per megaparsec. So this is in tension with the Planck CMB measurements by about 5 sigma now. Now, there are other ways to calibrate the distance ladder. So for example, using tip of the red giant branch measurements, there's a sort of competing collaboration called the CCHP team. They've gotten kind of an intermediate value of about 70 kilometers per second per megaparsec. But when you sort of sort all this out, it seems like when you calibrate your H0 measurement from early universe observations, so sort of, in the time of the CMB, sort of before recombination, those values tend to be lower, sort of around the Planck CMB value, whereas late time values, late universe measurements, and late here meaning just sort of anything after recombination, they seem to sort of cluster around the Hughes values, so sort of like around the low 70s, 70 to 75-ish. So the reason for this apparent discrepancy still is unknown. We don't know why they don't agree as well as they should. It could be there's some systematic error in one or both measurements. Or a more interesting explanation is that the flat lambda CDM model, which we had to assume for the early universe measurements, is actually not correct. And we need new physics to explain that. So the key to understanding this Hubble tension is that we need as many independent measurements of H0 as possible to try to sort through and test for systematics. So one way to get an independent measurement is through strong gravitational lensing. So in strong lensing, there's a technique called time delay cosmography, which I'll explain briefly here. So when you have multiple images of the same background object due to lensing, you get a time delay between the multiple lensed images. So the reason for that is that the light rays that travel from the source to the observer along different images that you observe, there's a slightly different path length that the photons travel, and there's a slightly different gravitational potential that the photons pass through. So this leads to a delay in the arrival time of photons depending on which image you see it at. So two photons that get emitted at the same time from the source but arrive at the observer through different images will arrive offset in time. Now you can actually measure this time delay if the source is variable. So for example, if it's a lens quasar, and I'll explain more about that in a bit. Now the expression for the time delay is given by this equation here on the right. So it's just saying that the time delay, t, is equal to the product of these two terms. So this first term, d delta t, is what we call the time delay distance. This is just a combination of angular diameter distances between the lens, the observer, and the source. And each one of these angular diameter distances has a factor of 1 over h0 in it. Okay, so this whole thing is proportional to 1 over h0. And the second piece of the time delay equation is what we call the Fermat potential. So this is sort of a scaled version of the gravitational potential of the lens. And you can calculate this from your lens model. So when you determined the mass model of your lens, the mass distribution of your lens, you can calculate this Fermat potential from that. And so to sort of simplify this, the idea behind time delay cosmography is that if you can measure this time delay, delta t, and determine the Fermat potential from an accurate mass model of your lens, then you can solve for this time delay distance term, and therefore this is proportional to 1 over h0, so therefore you can solve for h0. Okay? So in practice, how do we measure this time delay t? So if you have something variable like a quasar, these are variable on timescales of days. So if you were to just observe a lens quasar and take an image of it every day or every few days and measure the brightness of each of the 4 images over time, you can build up these light curves of each of the 4 images. And what you're looking for in these different light curves are features that correspond to the same brightening or dimming event at the source. So in this particular movie, the source is going to get brighter all of a sudden in image B right here. So you see this brightening in image B first, and then it happens a few days later in image A, then image C, then image D. So this arrow is going to indicate that brightening there. So you're just looking for features in these light curves that match up. And then you can just shift those curves until those features overlap. And the amount of the shift tells you the time delay of this lens. So sort of a quick summary of time delay cosmography. In order to constrain H0, you need these pieces. You need them to measure the time delay. You need high resolution imaging to get an accurate lens model. So that's how you determine the Fermat potential. You need to estimate the mass along the line of sight because this can induce perturbations. So this is called external convergence, this kappa external term, and I'll talk about that a little later. This can actually induce a bias in your inferred time delay distance. And you also need stellar kinematics of the lens galaxy. This sort of helps break some degeneracies in the lens modeling procedure. So I've been working as part of the TD Cosmo collaboration. So TD Cosmo, it was originally called Holy Cow, so you might see a few of our earlier papers under that name. But this project is performing a detailed analysis of time delay lens quasars using a lot of data and a lot of new techniques that we've developed. So in our latest results, we have analyzed 8 lenses, these 8 being shown here. And we want to point out that the lenses, other than the very first one, were analyzed blindly with respect to key parameters. So these were analyzed without knowing the values of H0 we were going to get until after the lens was ready to be published. So I'll talk a bit more about that as well. So I will go through a bit of the TD Cosmo analysis and maybe some of the history of our H0 measurements. So first, the time delay measurements. I already showed the previous movie showing how we measure the time delays. So now this one is another TD Cosmo lens with our actual data showing the light curves of this lens. So these light curves, if you notice, it starts in 2003 and it goes all the way to 2020. So this is 17 years of monitoring. So we have very long light curves to get pretty precise time delay measurements. We use a bunch of small 1 and 2 meter telescopes to do the monitoring. And we've developed a lot of algorithms to fit the light curves and get accurate time delay measurements. We've also been doing some high cadence monitoring. So I'm using a slightly larger telescope. The reason we need such a long baseline normally is because you can actually have micro lensing due to stars in the lens galaxy. So this can mimic features in your light curve. And so in order to overcome that, you ideally want to have several years worth of monitoring. But we think that with high cadence monitoring, so taking an image every single night for maybe just 1 or 2 seasons, you're kind of catching much smaller variations that are not affected by microlensing. And so that looks pretty promising. And hopefully moving to the future, we won't need decades of light curves. We can make do with 1 or 2 seasons. So that will speed up the process quite a bit. The next part of the analysis is the lens model. So we use high resolution imaging from either HST or more recently JWST or ground-based adaptive optics imaging. And the reason we need such high resolution is because we want a very detailed mass model. And if you kind of look at this figure I'm showing here, this is one particular lens that I modeled. On the left column, we're showing the HST data. The second column is our best fit model reconstruction in each of the 3 filters. So we want our model to match the data as best as possible. And when you subtract the 2, we get the residual in the 3rd column. So these residuals, you want to minimize that. And then the final column on the right is the reconstructed source. So this is what we think the source galaxy should look like if there was no lensing. So if you kind of notice, obviously you see the 4 quasar images, but underneath the 4 images of the quasar, you sort of see a faint ring. That's actually the host galaxy of the lensed quasar. And you can use the full surface brightness distribution of that, that host galaxy as constraints on your lens model. So you're not just using the quasar positions themselves to constrain your mass model. You're actually trying to use every single pixel in all 3 bands underneath there to kind of reconstruct to this coherent source on the right column. So this gives you many more constraints than just the quasar itself. We also test and compare different lens modeling codes to make sure that they agree, make sure we're not biased by a particular choice of software. So in our modeling, we typically assume either an elliptical power law or what we call a composite profile. So this is the stack of an NFW profile to represent dark matter and a stellar profile, which is linked to the light distribution. And just sort of example here of those two model families. So the power law is just a single power law in density of the lens galaxy. And the composite profile, it's the sum of these two components, the stars plus the NFW halo, which will sum up to create something fairly similar to a power law as well. And I will describe a little bit later how we sort of deal with these two different model families. And then we also have to account for mass along the line of sight, because if there's some galaxy or group or cluster along the line of sight, those can create this bias that I mentioned earlier called external convergence. And you need to account for that, or else your final result is going to be off by some factor of what we call kappa external. It's sort of this extra mass that you would, due to line of sight structure, you can't constrain directly through the lens model itself. So we sort of know that lens galaxies lie in overdense environments. That's because lenses tend to be more massive galaxies. The more massive a galaxy is, the more likely it is to be a lens. And those galaxies tend to cluster more. So we know that lenses on average are in overdense lines of sight. And some of the galaxies nearby the lens need to be included explicitly in the lens model itself. They're just too close or too massive, and you can't approximate them through this external convergence term. But there's also all of the other weaker perturbers along the line of sight. And so to account for those, we use sort of a weighted galaxy number counts method calibrated by cosmological simulations. So the way that works is we can take an aperture around the lens, maybe say 2 arc minutes or so, and then we count up all of the galaxies in that aperture above some flux limit. So then we have the number of galaxies around the lens in that radius above some flux limit. Then we go to a survey using the same observational setup. We take similar size apertures in random lines of sight in the survey, and we ask, okay, what is the number of galaxies in each of those lines of sight? So this is trying to get random lines of sight to represent the distribution of lines of sight in the universe. And then we ask, how overdense is the lens galaxy's line of sight compared to the average in the universe? So we have, it's sort of the ratio of the number of galaxies in the lens galaxy aperture versus the mean of the number of galaxies in the survey aperture. So there's relative overdensity. Obviously, if it's 1, that means it's a totally average line of sight. If it's higher than 1, it's overdense. Then what we can do is we can go to a cosmological simulation where we know where all of the mass is, and then we pick out lines of sight in the simulation that have that same relative overdensity in number counts as the lens does. And we just take that distribution of fields in the simulation and then calculate the external convergence in those lines of sight and use that distribution to account for this external convergence term. So here's an example on the bottom right here. So this curve is the distribution of kappa externals, external convergence, that we calculate for one particular lens. So this one, you see the peak is kind of around 0. So maybe you think it's a little bit, it's a fairly average line of sight. It's actually a little bit overdense because there's a higher tail towards higher values, but it's pretty close to average, slightly above average. And we get a median and a distribution. And this is essentially applied to our result in post-processing as an additional bias and scatter in our inferred time delay distance. We've also, in 2 of our fields, we've done an independent weak lensing analysis to constrain the external convergence. And in both of those cases, the value agreed with our weighted number counts method. So sort of using these procedures that I mentioned, our previous results, we got a value of h naught that was about 73 or 74 kilometers per second per megaparsec with a 2% precision. So whether you marginalize over the different model families, so combining the power law or the composite models together, or whether you take them separately, you get about the same result either way. Now, one thing to understand about this result is that because you're assuming this explicit form of the lens galaxy mass profiles, whether it's the power law or the composite model, you are sort of implicitly fixing the mass density at all radii in your model, even though you're only really constraining the part where you have lensing information, right? So if you're using, say, a power law model and your lensing tells you that the power law slope is, whatever value, say, -2 or something, well, that model is going to explicitly tell you what is the density at any other radius because you've made that assumption of the profile. And so if real galaxies are not actually represented by either of these models, if real galaxies are not actually a power law or actually a composite model, this can create a problem because there's this thing in lensing called the mass sheet degeneracy. So the idea behind the mass sheet degeneracy is that it's possible to multiply the density profile of your lens by a multiplicative factor, which we call lambda, and at the same time rescale your source light distribution, what's going on in the source plane. And if you you scale the density profile of your lens and scale the source plane by this factor lambda in just the right way, what can happen is that you can leave all observables invariant, but change your time delay. So this can create a bias because now you're getting a different time delay with the exact same lensing observables. Now, the source plane in practice is not observable. You can never know what the true source plane looks like. And so this is sort of a fundamental mathematical degeneracy in lensing. Now, this can be due to either an external mass sheet perturbation, so this external convergence I mentioned, or it can be due to a modification of the lens mass profile by this factor lambda, or lambda internal, we call it. And so this can lead to a bias on your inferred H naught by this same factor lambda if you don't account for this. Now, I mentioned when you assume a particular mass model for your lens, like you assume a power law or you assume a composite model, you are implicitly breaking this degeneracy by asserting what is the mass density at every radius from the center of your lens galaxy, even though you've only constrained it with a small radial bin, essentially, using the lensing information. Now, the way to mitigate this or break it partially is through stellar kinematics. So if you can measure the velocity dispersion of your lens, this actually gets you another constraint at a different radius from where you have lensing information. And by combining the lensing information with kinematics information, you can significantly mitigate this mass sheet degeneracy. And so what we did is we sort of took our previous TD Cosmo analysis and we did an analysis of the exact same data set, but allowing for a free lambda internal. So we can parameterize the mass model of the lens by explicitly including this mass sheet degeneracy term, lambda internal, in the mass model itself, and only allowed to be constrained by kinematics. So this is sort of the most conservative assumption we can make. Now, just having the total integrated velocity dispersion of any individual lens galaxy isn't really sufficient to make this constraint, because there turns out to be a degeneracy between the mass of the lens and the anisotropy of the stellar orbits. So the way we did this is through a Bayesian hierarchical framework, where the cosmological parameters, such as the Hubble constant, and also this lambda internal and the galaxy anisotropy parameters were all sort of treated as hyperparameters at the population level. So there's sort of this global, we have a global H naught, obviously, and a global lambda internal distribution, and a global anisotropy distribution, and sort of forward model these in a way using the constraints from the TD Cosmo lens sample. Now, one benefit of this approach is that we can bring in external data sets, including non-time delay lenses, to constrain these hyperparameters. So even if you have, say, lens galaxies, which don't give you any time delay information, they can still help you constrain these other parameters that are correlated with H naught. So we sort of did that by using this sample called the SLAX sample. These are some lower redshift objects, but observed with HST. So these are more galaxy scale lenses. And so when we did that, we sort of knew the constraints would be not as precise because we're making a very conservative assumption here by only allowing lambda to be constrained from kinematics. But when we did that, what we found is that the constraint on H naught went from about 2% to about 8%. So that's sort of this blue point here. So 74.5 with a constraint of about 8%. So again, this is sort of the maximally conservative result. Now, the interesting thing at the time is that when we brought in the external data set from SLAX, the error bar went down to about 5%, but the central value shifted to something lower, like 67.4. So statistically, it was still consistent. It just seemed to, now it seems to agree more with the CMB value. But actually, it turns out when we did some more recent investigation, it turns out the reason for this shift was actually that there were some problems with the velocity dispersions in SDSS at the time. So SLAX was drawn from SDSS. And those velocity dispersions are biased due to insufficient signal to noise in some of the template libraries used to make the measurements. And so we think these are actually not reliable for precision cosmology. So this result we no longer think is trustworthy. Okay. So sort of based on what we learned from these previous results, we thought that our focus moving forward should be to really improve our stellar kinematics, because it seems like that was the way to really address this mass sheet degeneracy and get this error bar back down as low as possible, even accounting for the full mass sheet degeneracy. So with TD Cosmo 2025, this is our latest paper that was just released a few weeks ago. This is the culmination of the last few years of work we've put into this. So compared to the previous results, we added the 8th lens to the sample. So our sample size is now 8, up from 6 or 7. And the big change aside from that is our updated kinematics to address the mass sheet degeneracy. So we've gotten some updated measurements for SDSS spectra. So using, for example, Keck IFU data. We've also got new data from JWST NearSpec as well, and VLT Muse, especially some IFU data to get spatially resolved stellar kinematics. So that's a really big help. And we fixed a lot of these problems we found in the past due to stellar templates having problems with signal to noise or other features. And we're accounting for things like triaxiality and projection effects to model the stellar kinematics. We've updated our hierarchical analysis. So now instead of using this SLAX sample, we're also using a separate sample called SL2S that we think might be better matched to TD Cosmo lenses. So you do have to assume in all of this that your TD Cosmo lenses and any external data sets you use that those lens galaxies are fundamentally drawn from the same family of galaxies. And that's an assumption you just have to make or be fairly confident in. So we were much stricter this time in how we selected the galaxies from these 2 external lens samples to make sure that they agreed with with the TD Cosmo lenses in various parameters. And also we sort of homogenized the hierarchical analysis of our line of sight structure. And again, this is all done blindly with respect to the key parameters that we care about. So the new kinematics measurements, I'm just going to show a few spectra here. So here is some JWST near spectra on our lens galaxies on the left. And on the bottom right is actually the JWST near spec IFU data for one of the 8 lenses. So this is the only one we have. We finished the analysis of the IFU data for so far, but we do have IFU data for a few others that are sort of in progress. So you see it's very high quality spectra. We're pretty confident in the velocity dispersions from this. We think we can get to better than 1% accuracy in our velocity dispersion measurements from these data. The external lens samples I mentioned. So again, we were much stricter in terms of which external lenses we chose. So the previous analysis in TD Cosmo 4, we had 33 SLAX lenses. This time we only have 11 plus 4 lenses from SL2S. And it's just because we want to make sure, we really want to make sure that the lenses we pick to constrain these hyperparameters are as close as possible to TD Cosmo lenses in things like redshift, velocity dispersion, effective radius, and a few other parameters being shown here. And of course, we've improved the data for a lot of those external lenses as well as the TD Cosmo lenses. And then finally, I mentioned the blind analysis. So when we say blind analysis, what we mean is that whenever we're modeling a particular lens or doing a particular analysis, we always blind the value of H0 or any related parameters, meaning that when we're looking at plots or looking at tables, we always either subtract off the median of the distribution or set the median to 0. And so in doing this, we never actually see the value of H0 we're getting, the absolute value, but we can still see covariances with other parameters, and we can see the spread of the distribution. And the reason for this is just to avoid confirmation bias. So we don't want a situation where if we expect H0 to be, say, 73 or something, maybe we're doing our analysis and we get to a point where H0 is 73, and we think that okay, we're finished. We can publish this now. By blinding our analysis, we have to be very confident in our systematic error checks and very sure that we've done everything we can to improve the analysis before we're ready to unblind. And once we're ready to unblind, all of the principal authors on a paper have to agree. And the agreement is that once we've unblinded, we have to publish that result with no further modification to the analysis. So here's an example of how we might do the blinding. So on the left plot here is an H0 distribution for a particular lens, and you see it's centered on 0. So I've just subtracted the median here. So we don't know what value of H0 it's centered on. And then once we unblind, I just make the exact same plot, but showing the actual value here. And once we show this and we have the value, that's the value that gets published with no further modification. So together, I can now show you the results for TD Cosmo 2025. And so again, this is still using the free lambda internal. So this is the conservative mass model assumption allowing for the full mass sheet degeneracy. And we consider our primary result to be the TD Cosmo lenses alone, plus a prior from the Pantheon supernova sample to constrain omega matter. So that's this first orange point on top here. So we get a value of 71.6 kilometers per second per megaparsec, and it's constraint of about 5% or so. When we combine with the external data sets from SLAX and SL2S, we had a slightly lower error bar, maybe 4.5%, and the central value shifts to about 74.3, but it's still within 1 sigma of our main result. So putting this in the context of the Hubble tension, so now I'm showing you some of the main results from the early and late universe. So again, the early universe results are all around the Planck value, about 67, 68. And the late universe results, I'm showing now the SHUs and CCHP results. So these are the two main distance ladder results. I think the TRGB surface brightness fluctuation, I believe that's a third team, but they're also getting something with a central value, close to that result. And our result, even though statistically it is compatible within 2 sigma with Planck, it is closer to the late universe results, especially if you combine with these external data sets. So we can look at extensions to flat lambda CDM as well. So this is just a couple of the alternate cosmologies we tested. If you look at our paper, there's a few others. But if you allow for, say, a time varying W, then you can get constraints on simultaneous constraints on H naught and the equation of state parameter W. You do have to combine with other data sets like Planck or BAO to get sort of meaningful constraints. TD Cosmo alone doesn't give you particularly strong constraints on W, but in combination with the other data sets, you can. And so this is sort of what we just released within the past month or so from this milestone analysis. So moving into the future, our ultimate goal is to get down to about 1% precision on H naught. So to do this, we're proceeding in a few different directions. So we're going to use new data from JWST, both imaging and spectroscopy. So we just started working with JWST NIRCam imaging data, and the first paper presenting a lens model from that, this Williams et al. 2025 paper, it's on arXiv, and I think it will be accepted very soon. So the results from that are pretty promising. And JWST NIRSpec, especially NIRSpec IFU data for the remaining TD Cosmo sample, we think will really nail down this mass sheet degeneracy and constrain lambda in much better for the entire TD Cosmo sample and get this error bar down to below 5% and hopefully approaching 1% once we improve the sample size. We're also incorporating new techniques and methodologies. So we've explored a combination of weak and strong lensing to try to constrain the mass profile, to constrain this, this mass sheet degeneracy. And we've also started looking at double image lenses. So all of the lenses in TD Cosmo so far are what we call quad image lenses. So meaning 4 images rather than 2. And that's partially for historical reasons. Quads are just easier to detect, so we know more of them. But actually doubles make up most of the lenses in the universe. And so we want to make sure we don't have any selection biases by focusing on quads. So the first paper in TD Cosmo to do a full analysis of a double image lens is about to be released. So actually my postdoc, Eric Pike, is leading this analysis. And in the future, we're going to have much larger lens samples. So moving into the era of LSST, Euclid, and Roman, there's eventually going to be hundreds of thousands of lens quasars for time delay cosmography. And also lens supernovae are becoming an interesting source of constraints using time delay cosmography. There's a couple analyses using cluster lens supernovae. And in the future, maybe we'll be able to use a few from at the galaxy scale as well, once those are discovered by these large surveys. So to account for all of that, this incoming data, these huge lens samples coming in, we have to develop lens search methods on large imaging surveys, such as DES and HSC, sort of in preparation for LSST and beyond. And also the lens modeling itself takes quite a bit of time. So we need to speed that up somehow. So we're developing some automated modeling techniques to get at least preliminary constraints on some of these mass models. So that's sort of the end of the first portion of my talk. How am I doing as far as time?
You have 15 more minutes.
Okay. Okay, sure. So I will just go briefly then through the second part of my talk. So, so talking about these these incoming data sets. We do need more lenses to increase the sample size, not just of lens quasars for time delay cosmography, but you could do a lot of other science with lenses as well. So you kind of want a statistical sample of lenses of all types, galaxy scale, cluster scale, with galaxy sources, quasar sources, and ideally across a range of redshifts for multiple science goals. So you want to study things like dark matter or galaxy mass profiles or dark matter halos. You want to have large samples of lenses with a range of properties. And so you need deep, wide area, high resolution imaging to improve these statistics. So, so I've been working as part of the Subaru Hypers Prime Cam survey. So the Hypers Prime Cam is an instrument on the Subaru telescope in Hawaii. And so HSC has just completed this HSC SSP survey, which covered over 1,000 square degrees in GRIZ widebands to a depth of about 26 magnitude. And the median seeing in I-band from Subaru is 0.6 arcseconds, so quite good. So this is an ideal data set for discovering new lenses. So I'm one of the co-chairs of the HSC SSP Strong Lensing Working Group. And we have various methods for discovering new lenses. So our lens search program is called the Survey of Gravitational Lens Objects in HSC Imaging, or SUGOI for short. And we have a public catalog, which you can view at this website here on the bottom left. And the different methods we've used, we've got some automated algorithms for lens finding. We've done some variability searches, spectroscopic searches. We use citizen science, and more recently we've explored some machine learning techniques as well. So to date in HSC, we've found about 1,000 galaxy scale lenses up to about a redshift of 1, which includes about 30 lens quasar candidates and about 300 group and cluster scale lens candidates. So one nice thing about the Sugoi lenses is that they tend to be at a higher redshift than similar samples. So the main competing survey is the dark energy survey, and that's a wider area but shallower. So even though maybe they're finding more lenses are at a higher redshift, they tend to be at redshift greater than 0.5. So this allows us to study the evolution of lens properties over time. So just a few science papers that we've done in the past with these lenses. So I did a study of lens galaxy environments and lines of sight out to redshift 0.8, just comparing the Sugoi lenses to a control sample of sort of twin galaxies. So lenses matched in redshift and velocity dispersion, but that are not lenses, to see whether lenses lie in overdense lines of sight. It appears that there's some evidence they might be slightly overdense compared to these other twin galaxies, but it's marginal significance. There's no evidence for redshift evolution of the local overdensity of lens environments over time. So in HSC, we made an interesting discovery of a double source plane lens being shown on the bottom here. So this double source plane lens we call the Eye of Horus. So here you see actually two sources being lensed by the same galaxy. There's sort of this inner red arc, like an arc and counter image indicated by the green arrows. And then both of those are lensing a second source, which is the blue ring around it. So this kind of gets you extra constraints on your lens mass profile and on cosmology compared to typical lenses. And we've also explored lens transients, so using a variability-based lens search. Again, I mentioned that in the future, lens supernovae could be an alternative to lens quasars for time delay cosmography. So this variability-based lens search, it was sort of done on some mock data, but it demonstrated the possibility for future samples such as LSST, which will discover hopefully maybe tens of lens supernovae at the galaxy scale to make these constraints. So I'll talk briefly about some of our more recent lens searches using machine learning techniques. There have been a few papers both within the HSC collaboration itself and also using the public data by external collaborators to search for lenses in the HSC survey using neural networks. So Neural networks provide a fast and efficient method to search these large imaging data sets for lensing features. So the idea is that you train the neural network on a sample of mock lenses and non-lenses so that it can distinguish between the two. You use mock lenses that you construct to mimic realistic Sugoi lenses. You have to use mock lenses because we don't have enough real lenses in the survey to form an adequate training sample. But if your mock lenses are good enough, you can teach the network to distinguish between real lenses and non-lenses in the actual data. And you can actually combine different neural networks in a consistent way to improve the performance. So there have been a few papers that have come up with their own various networks. The main ones are these two papers by Cannamaris et al. And Xu et al. These are sort of our external collaborators who worked on the public data set. And then within the HSC collaboration itself, there were two main networks. One was developed by my collaborator Anton Jelani in Indonesia, and another was developed by actually an undergraduate student. He's now a master's student working with me here at the University of Tokyo, Yuichiro Ishida. And so we also had a paper comparing the performance of these four independent networks. And the idea was to see, not just which networks performed better, but what they had in common in terms of the lenses they got correct and the lenses they missed, and also the various strengths and weaknesses of the different networks. So each one, so the Cannamaris and Xu papers constructed their own mock lenses and their own non-lens samples, whereas the Jelani and Ishida papers, they also constructed their own, but those two shared the same mock lenses and non-lenses. And so to compare them, there's a couple fairly standard metrics we use to evaluate the performance of a neural network. So first, to calculate the true positive rate and false positive rate of a particular network. So true positive rate is just the true positives divided by true positives plus false negatives. So this is just the number of times the network got a lens correct divided by the number of times it thought something was a positive. And then there's the false positive rate, which is the number of times the network thought something was a lens when it actually wasn't, divided by the number of times the network thought something was not a lens, whether it got it right or not. And then you can sort of plot these two against each other to make this curve here on the right. So this is what we call the AOC or the ROC, the receiver operating characteristic, as a function of threshold. So threshold meaning how sensitive your network is to calling something a true lens or not. And the idea is you want your true positive rate to be as high as possible and your false positive rate to be as low as possible. So you would like to be as close to the upper left corner of this plot as possible. And how well your network performs across various thresholds is represented by the area underneath this curve, which we call the OROC, area underneath the ROC curve. There's also a few other metrics to use, but this is sort of the main one. So when we sort of compared the four different networks what we compared them on is we had a common test sample. So this was a test sample of real lenses and mock lenses that was hidden from all four teams until we were ready to compare. And then once all the networks were ready, we all ran our networks on this common test sample of real lenses and real non-lenses, and then see how we performed. And so different networks performed better or worse depending on the test sample. It turned out the Cannamaris and Xu networks performed slightly better. It also turned out that some of the common characteristics of the lenses missed by the majority of the networks are pretty interesting. So I'm showing a sample of some of the common test sample lenses here. And the ones marked in blue are the ones that all four networks got wrong. So these are real lenses that were not correctly identified by all four networks. And so it tends to be either red arcs, so these are very rare red sources. Most sources tend to be blue. Or in some cases, it's a very compact, high redshift lens galaxy where maybe you can't correctly separate the lens and the source light, or the colors are slightly off. Or in some cases, it's a very wide image separation. So part of the lens fell outside of the image cutout, so you couldn't actually see the second image of the lens. So that's why it failed. So that was interesting. We also looked at the impact of different training samples. So so my student Yuichiro Ishida took his network and tried retraining it on the training samples of the Canameris and Shu papers without changing anything else about his network. And what he found, interesting thing, was that he actually outperformed those two samples, especially the Canameris paper. He outperformed Canameris et al. On their own training sample. So, Canameris et al. Trained his network on his training sample, but a different network trained on the exact same training sample performed better, even though in principle his network should have been optimized on his own training sample. And we think maybe it's because that the Shu and Canameris papers used what we call a residual neural network, whereas the Jelani and Ishida networks were more classical CNNs. So maybe there's some flexibility in the classical CNN architecture that allows it to adapt better to differences in the training sample that maybe isn't captured by the residual networks. So that's a possibility. And then finally, my student Yuichiro Ishida also looked at the possibility of subtracting the lens galaxy light before training as a possibility to improve performance. So what he did is he used a software called Yatta Lens to subtract the central light from each of the images. So here's an example here where he's trying to subtract the lens galaxy light from a real lens. And if you have a non-lens, it'll just subtract off the light from whatever galaxy is there. And then try to train on those light subtracted samples. And then when you look at the real data or the test data, you perform the same subtraction on that data and then see how well can the network identify lenses and non-lenses compared to when you look at the original data. And it turns out the best performance is when you sort of stack the original, the fiducial HSC data with the light subtracted sample. So instead of using just like GRI band images for the neural network, you use GRI band images plus the GRI band light subtracted images. So 6 images total for every object. That gets you a slightly better performance than either the fiducial data or the light subtracted data alone. So so that was also one thing that we tested. So I think I'm coming up on the end here. So I have my summary slide. Time delay cosmography with lens quasars provides a late universe measurement of the Hubble constant that is completely independent of the CMB and the distance ladder and type 1a supernovae. So the TD Cosmo results from a total of 8 lenses can attain a 5% precision measurement of H0 in flat lambda CDM. And this 5% precision is maximally conservative with respect to galaxy mass profiles. So our result is consistent with the type 1a supernovae and distance ladder measurements. And it is consistent at sort of the 2 sigma level with the CMB measurements as well. But we think that we can push toward a 1% constraint by increasing the sample of lenses, including double lenses, and getting resolved kinematics for the entire sample. And moving forward, we need to incorporate automated lens modeling to speed up the modeling of this large increase in sample size. And we also have to discover a lot of these new lenses, and some of the ways to discover that we've already developed within the HSC SSP using things such as neural networks, try to identify characteristics of the lenses that we can that we miss sometimes with neural networks. And that the combination of different independent network architectures and training procedures are going to be needed to fully explore the discovery space to maximize the sample size that we get out of both the current surveys like HSC and upcoming surveys such as LSST, Euclid, and Roman. So I think I will end there, and I'd be happy to take questions. So thank you very much.